All right, now we're going to work through an entire example of a higher order function in grisly detail. Ready? Buckle your seatbelts. So the function that we're going to be looking at is this one right here, x to the fourth plus y to the fourth minus 4xy plus 1. And the domain we're going to be looking at is minus 2 to 2 for x and minus 2 to 2 for y. So we're on a square that's symmetric around the origin with side length 4. Okay, so let's see. So step 1, we do first derivative test. So for that, we're going to need the gradient. So we compute the gradient of f, and we get 4x cubed minus 4y. And for y cubed minus 4x. So if we set this equal to 0, so I actually mean 0, 0 here, but it's common to denote the origin just by 0. Then let's see. We're going to get, so the first coordinate being equal to 0 is 4x cubed equals 4y. And canceling the 4's, we just get x cubed equals y. And then we also, from the second coordinate, get the corresponding equation y cubed equals x. So if I substitute one of those into the other, then that gives me the equation. And by the way, at this point, you're just messing around with algebra. Yeah, in general. So you get some equations coming out of the gradient being set equal to 0. How do you solve those? I don't know. Good luck. Mess around. It's basically ad hoc. You can get a lot of mileage out of substituting one into the other. So that's what I'm going to do. Substituting one equation, that is, into the other, assuming you can solve it for one of the variables. So if I put that y is equal to x cubed in here, then I end up with x equals x to the 9th. And what can I do with that? So x to the 9th minus x is x times x to the 8th minus 1. And I can use a difference of squares on that. So that becomes x to the 4th plus 1, x to the 4th minus 1. And then I can use difference of squares on this second term here, or the second term in parentheses anyway. And this becomes x squared plus 1, x squared minus 1. And then I can use difference of squares on that. Again, let me save myself some time here. And I get x plus 1, x minus 1. Okay, and so we're looking for the zeros of this thing. Right, because we started with this equation up here, so we subtracted the x over to the other side. And so we see that we're going to have the situation when x equals 0, or when x equals minus 1, or when x equals 1. Those will give us zeros. Similarly for y, because this equation is symmetric in x and y. So let's see. The critical points are going to be minus 1, the origin, and 1, 1. So now we proceed to the second derivative test. So for the second derivative test, let's see. We'll need the second partial with respect to x. So we do ddx of this guy, and so that'll be let's see, 12x squared, and then ddy of this guy. So that will be 12y squared. And we'll need the mixed partial derivative. So that's going to be, let's do ddy of the df dx derivative. And so for that one, we just get minus 4. So we know that our D is going to be given by, let's see, so the product of those first two is 144x squared y squared. And then we subtract the square of fxy, which is 16. Okay, so let's see. So if we evaluate this D, now D at the origin, now in this case, you see, since we started with a higher order polynomial, or a higher degree polynomial, we don't have a constant, we actually have a function of x and y. And so that's the general situation, is that you have a function of x and y there. So let's see, so when we evaluate it, we get minus 16, which is obviously negative. And so that tells us that we have a saddle at the origin. And if we evaluate it at 1 or minus 1, well, x squared and x and y both appear squared in this expression, so it doesn't matter what the sign of them are, we'll get the same thing. So that's going to be, let's see, so we've got now 144 minus 16, which is 128. That is very positive. Then the other thing that we need to do is check the value of the second derivative of f with respect to x. And for the same reason as the when we computed d, in other words, since x appears with a square and y, well, doesn't appear at all, when we evaluate this guy at minus 1, and 1, 1, we get the same thing. And namely that's 12, and that is very much positive. So with these two pieces of information together, we can conclude that both of these are minima. And then the last thing to do is check to see what the actual value of the function is at this location and this location, and we get minus 1. Okay, so now at this point, and let me emphasize here, these are local minima. So now we have to check the boundary to see what's going on. So let's take a moment to pause and have a look at the function itself. Okay, so here's a plot, and here's a contour plot, so that you can see a little bit of the detail there, because it looks sort of flat. But this is what's going on, and so you can see just from the graph of the function here that the maxima does not occur in the interior. It's going to be at these points here. But it does look like perhaps these points that we found in the inside are minima, maybe somewhere around here and somewhere around here. So in fact, if I just sort of crop out this portion of the function right here and exaggerate the vertical scale so we can see what's going on, we have pants. So look at that, a lovely little pair of lederhosen. Not bad, right? So that's why this function is called the pants function. Actually, it's not. I just made that up. But anyways, so moving along, now we need to check the boundary, right? So for example, we will look at the trace where we set the value of, say, y equal to 0. So that'll be looking along this line right here in the back. And the trace we'll get from that will be something like this. And so we might expect to find a local min of the trace here, and then we'll have to check the endpoints of the trace here and here. All right, so carrying on with this, and then of course also for all the other sides. So this is part 3 of our method. So part 1, first derivative test. Part 2, second derivative test. Part 3, check the boundary. Okay, so if we check the left boundary, then this is going to be where we look at f of x minus 2. So we're setting, oh, I just realized I plotted my picture with the axes backwards. I guess I'm giving you the backside view. Sorry about that. Oh, terrible. It's the backside of pants. Okay. So we've got 17 plus 8x plus x to the fourth when we substitute y into that formula. And then that tells us that the derivative of the function along this trace here, well, the derivative of this trace, is just 4x cubed plus 8. And so if we set this equal to 0, now I'm doing single variable first derivative test, then that implies that x is the negative of the cube root of 2. And if we look at the right side of the domain, then this is where we've got positive 2 and 17 minus 8x plus x to the fourth. And the derivative on this side is going to give us, let's see, so we've got 4x cubed minus 8, again, for first derivative test, set it equal to 0, and then we get the cube root of 2. Normally, we would also look at the top and the bottom, but this function is symmetric here. So since the function is symmetric in x and y, and by the way, when I say symmetric in x and y, I mean that if you put in y for x and x for y, the formula that you get looks exactly the same. So if you interchange the two variables, you get the same thing. So in other words, like f of 2 minus 1 is going to be the same as f of minus 1, 2. And in the picture you can see that as if you were to reflect along this line here, the values on opposite sides of this line are always going to be the same. Okay, so that tells me that we can skip by using the shortcut of symmetry. Okay, so now let's see. So what's left? Oh, the boundary of the boundaries. So remains to check the corners. And so for the corners, let's see. So f of minus 2 and f of 2, 2, those are going to be the same. And if you crunch those through the formula, you get 17. And if we look at f of minus 2, 2 and f of 2 minus 2, those will also be the same, and those end up giving us 49. So it's pretty clear where those ones are, right? Poking way the heck up there. And so let's see. So to figure out what the max and min are, we just have to compute f at all of these locations. So let's compile our list. So back in the beginning, we found minus 1. And let's see what else we got. F of minus cube root of 2, 2, and f of cube root of 2 comma minus 2. Those ones both give us 17 plus 10 times cube root. Wow, that was a messed up 2. It's had a bad day. Which is something like 29.6. And then the other place that we found was at positive cube root of 2 comma 2, which if we do the symmetry flip would be 2 cube root of 2. At that one, it's 17 minus 6 times cube root of 2, which my pocket calculator tells me is about 9.4. Okay, so we have found all points of interest from the critical points. In this case, there was only the one critical point. And then we found the critical points of traces. I just realized I labeled the wrong thing there. That was the corners. What am I talking about? This was the critical points of traces. And then we had those corner points. And so now we just look for the biggest and smallest values on there. And so we see that the smallest value is -1 and the biggest value is 49. So we have a min and we have maxes. And so that's telling us that we have minimal points at the bottom here and here, and then maxima like we knew we were going to find at each of these corners.